Good afternoon, everyone. Thanks for joining me here this afternoon. I know it's a first session after lunch, so need a little motivation, but thanks for joining me here. I am Sagar Gaikwad. I work at Capital One. For those of you who are not familiar, Capital One is a large financial organization in United States. It's one of the top 5 credit card processing companies, credit card companies in America. I've been with Capital One for the last 2 years, managing their data engineering teams, data engineering platforms. Prior to that, I worked for 7 years in the semiconductor industry, again, managing and building data platforms or data products. So two years ago, before I start, I wanted to get assessment on how many here have cybersecurity background, are more interested in learning about implementing cybersecurity platform versus more interested in. So who's interested in the cybersecurity aspect of those? And who's more interested in like the streaming, ingestion? It's 50-50. Yeah, so a year and a half ago, me and my team at Capital One, we received a very unique challenge to solve. We had to build a platform at Capital One which would ingest our entire log data, a platform which could ingest that at real time, would enable machine learning intelligence and provide cybersecurity at real-time scale. So the challenge was unique in many ways, primarily because Capital One over the past few years have made a lot of progress in field of open source and contributions and embracing open source. But 2 years ago, our journey, we were very new to the journey. We didn't have a lot of open source committers in the company. We didn't have a lot of applications which we were built around open source. It was a huge cultural change as well. At the same time, the data or the log volume we were trying to process and the system was expected to process was fairly large. Just to give you an overall idea about the log volume or what we were expecting, let's go through some data. So 45 million, that's the total number of customers we have internationally. Our primary locations is America, but we have customers based out of Canada and UK. And these customers generate anywhere close to 7 million HTTP requests on their client-facing applications or their web requests on their client-facing application, mobile or web applications per hour. 45,000, that's the total number of employees we have at Capital One. And any given point of any given day, there are around 10 or 15,000 contractors coming in and out of our offices. And then you combine that with different operating systems, bring your own devices, mobile devices. It makes up a very complex infrastructure for us to manage. And these 45,000 employees and 45 million customers on a daily basis are generating, in form of like our web application or mobile application, close to 7 terabytes of data. So our application had to process that much amount of data at real time on a daily basis. So it had to be a scalable application. Cybersecurity has always been a top priority for Capital One for like multiple reasons. We are a financial bank. So with every new credit card, we issue, there's new personal or personal information we get for customers. There's social security, there's a lot of financial addresses. It's both our ethical and moral responsibility to protect that data. The data breaches, they're not cheap, they're extremely expensive. So we wanted to avoid those costs. At the same time, we had to protect the brand. So what did we have in place before we went on this journey or we went on building this real-time ingestion platform? So before we build the system, at any given day, our cybersecurity analysts were using anywhere close to 30 or so point solutions. They were these SIM solutions, vendor paid, like ArcSight or multiple vendor solutions. So during a forensic analysis or during some investigation, our analysts would have close to 30 application windows open on their screens. And they would be shuffling between. So if they're looking at, they would be looking at Blue Code log in one window. They would be looking at IronPort log in a different window. They would be looking at a different ArcSight log at a different window. We used to call that internally a swivel sharing. So it used to be very cumbersome and very difficult, like switching between these different screens for going through one IP. The analysis was very forensic. compared to being proactive. It used to be after the fact. Once we identify an IP breach, we would start investigating and then again have to go through these multiple screens. We had a rule-based system which would alert us or identify some of the breaches, but it was very static. Once the rule was set, it was very difficult to change it on the fly or change it once the data has been processed. So we had to change that. We wanted to build something which was more proactive, something which was more dynamic, and which was machine learning enabled. So Capo One launched this program called as Purple Rain in June of 2015. So all the principle, there's a background story where it was named Purple Rain, but I can share that after the session if you're interested. But this Purple Rain program, the whole initiative was to build this real-time capabilities, which would be architectured primarily built on machine learning. And it would also provide a single pane of glass for our cybersecurity analysts. So rather than shuffling through different screens, it would be a single dashboard which our analysts can look at and be notified about. And they can look at data that's important rather than going through hundreds or thousands of lines of log. So before we started building the application in-house, we actually did a thorough analysis of what was available out there versus this choice between build versus buy. So we looked at a lot of vendor solutions. We looked at a lot of open source technology which we could directly embrace. And we saw that a lot of those vendor solutions, a lot of open source technologies provided a lot of the features we were looking for. There were a lot of applications or a lot of solutions which process large volume of data set. A lot of applications, a lot of tools were cloud enabled. A lot of applications provided real-time alerting. But the key differentiator for us in deciding of building this solution in-house, the primary reason was it had to be machine learning. We wanted to make sure our machine learning intelligence was preserved inside. We didn't want to take on an application or a vendor solution which provided data science model. We wanted to make sure, because the data we were protecting was very sensitive, we wanted to make sure the models were built in-house. We provided the capabilities and it was preserved inside. At the same time, we controlled 100% of the feature list. So what happens is a lot of time when you're working with an Apache project, there's a lot of Apache governance which comes into place. There's certain guidelines you have to abide with. There's a release cycle you have to wait for. It's the same thing when you're going with a vendor solution. Each vendor has their internal roadmap, release dates. And we had our specific internal deadlines where we had to meet. So we wanted to make sure we control our sprint cycles, we control where the features were rolled out. At the same time, the application had to provide 100% of our requirements. So we saw there were a lot of solutions out there which did 80% or 70% of what we wanted. There was nothing in the market at that point which would do 100% of what we wanted. So we decided to build that application in-house. So once we had our basic core criteria which we wanted to build, plus we had the requirements, we had the core components of our MVP ready. We knew we wanted a platform which would have a layer, which would ingest large volume of data. We wanted a mechanism to queue that data, the incoming log data. We also wanted a layer which would further enrich that data with help of our internal machine learning intelligence, with help of our custom business rules. Then we wanted to persist that data. So we wanted a persistent layer, both for long-term and for short-term storage. Once the data has been persisted and been process enriched, we wanted alert UI mechanism where our analysts are alerted rather than they going and investigating. They are getting alerted when something of significance or a potential breach is identified based on our machine learning and business rules. And we also wanted to visualize that data in form where they can do some forensic analysis, which was more search-based, where if they have to do a further investigation, deep down investigation, they could do forensic analysis. So what you see here right now is how the architecture of Purple Rain stands in production today. There have been some iterations where we have swapped out few components in and out. But this is the actual state of production. It's been running in production for close to a year now. And this is how it stands in production. To the very right-hand side of the screen, you have a log aggregator tier. That's a custom in-house solution we built to collect the data. It's a Java-based agent which runs on every server, every machine, or every web application, and it's doing is collecting the data, collecting the log data, converting it into a syslog format, and then it forwards that data into an UDP protocol to our ingestion layer. Our core ingestion layer is powered by Apache NiFi. How many of you here have used NiFi, familiar with NiFi? Awesome. It's a great tool. It's a tool which came out of NSA. NSA built this solution a few years ago to process large volumes of files they had in-house for analysis. So when Joe Witt and his team came out with this open source solution, it was backed by Hortonworks. We were one of the early adapters of this solution. I think we partnered with Hortonworks right when this project was incubated. We had some minor glitches because it was a new Apache project, but it's been pretty solid since last 1 year. We use this as our core routing transformation layer. We have, for each data sources, we have a separate workflow in NiFi. It has a very easy to use web UI, drag and drop. You need very minimum programming experience, but it's under the hood is all Java objects. So if you want to extend, we've extended for some of our custom processors or some of the custom logic, we were able to easily extend it. So it's very easily extensible. So we have 2 instances of NiFi in our production environment. And the reason we have 2 is more of the governance reason. So our data needs to be ingested directly on-prem. That's more of a governance and audit requirements we have. We can't send the data directly to cloud. So we have an on-prem cluster, which is the primary collector. It's a 3-node, 22 CPU, 375 GB memory cluster. The data is being collected, tagged, and then sent to AWS. On AWS, we have 6-node cluster. They are M4 4X large machines. As I said, for individual data sources, we have a different unique field, so it helps us differentiate the data flow very easily. It's been very stable in production. As you can see, I mean, we've been processing 7 terabytes, and we've had, apart from the initial glitches, it's been pretty stable. Kafka, again, it's a battle-tested, proven message queue. We use it for our publish-subscribe model. For every data source we have in our ingestion pipeline, we have a separate topic in Kafka. And further, based on some of the Metron architecture, we have separate topics for enrichments as well. We have 20 brokers, again, M4 large, 250 EBS volume machines. We have a replication factor of 2. We have done some optimizations on partition just for scaling it as well for processing throughputs. And Storm is the underlying core streaming engine we have, which we use for parsing the data enrichment. So we have separate different bolts, which we use for enriching, parsing. We have a 45-node Storm cluster, again, M4 2X large machines. We have a Storm Nimbus UI, which is a M4 2X large, 4 worker slots per node. So Metron. Metron is a core or the core component of our framework. It is an abstraction layer built on top of Storm. What it does, it gives you an ease of building Storm topologies. It takes up a lot of the overheads you would otherwise would have. If you're building the same application using just core Storm, you would have to write all those parsers. It takes a lot of those overhead out of it. A lot of those parser creations are in form of configuration. So you make small configuration changes and you can build new parsers. It is broken down into 2 core components, a parser topology and an enrichment topology. The parser topology is the topology which takes in the data, standardizes, converts it into a standard JSON format, and then you have specific tags. And then you have enrichment topologies, which again consume the parsed data, and then you can further enrich the data with, if you have internal insights you want to add, or based on some external vendor insight, you can add them. Metron originally used to be called OpenSock, which was again backed by Hortonworks. I think sometime last year, they took on Metron. It was incubated. I think it is in the process of getting moved to a top-level project very soon. We've been a core contributor. We've been using Metron for some time. Some of our team members are also contributing back to some of the Metron code base. This is the basic Metron logical architecture. I mean, it's very similar to the architecture diagram you saw earlier, where NiFi it powers the ingestion for your platform. And then you have a buffering layer, which you can be, in our case, it's Kafka, and again, it's the Apache Metron recommended way as well. And then you have different layers which the data goes through. It gets processed, enriched, labeled, and you have an alert UI layer, which your analyst or based on your use case, your end users can visualize for. And then it has multiple data integration point. It has multiple data persistence point, depending upon. So what we've done is we use Metron as our core component. We've leveraged a lot of the components, but we have also added some custom components. And few of the reasons being the timeline on Metron, some of being we wanted to make sure, as I mentioned, the machine learning component, we wanted to make sure we build it and keep it in-house because of a lot of the IP we wanted to store. Also, the alert UI, we had some custom requirements from our internal customers. So we ended up building alert UI in-house, which was very easy to integrate with the core Metron framework. Same with the machine. So Metron provides a machine learning model as a service component, which you can use to productionize your machine learning models. But we ended up building our own because internally we have a larger initiative to provide a central machine learning as a model service, just not for cybersecurity, but other use cases too. So for that very purpose, we built a separate component. So we are not leveraging those two components of Metron. We build our own, but that gives you an idea how easy it is to customize and just embrace it and just also make it your own. So as I mentioned, there are multiple layers where you can persist this data. It has a lot of endpoints. It has endpoints for edge-based built-in. It has endpoints for Elasticsearch, endpoints for, in our production use case, we persist the data for long term. We persist in S3. So the raw data as it is coming in the production pipeline goes through, it's stored in SE, and that's our long-term storage, forever storage. For short-term storage, we index that data in Elasticsearch for 30 days. And that's the data which our analysts are using for doing some short-term forensic analysis when they find some infected IPs, and if they want to do some forensic analysis, they're using Elasticsearch. So Elasticsearch is under the hood is Lucene. It's very optimized for search and analytics type of function where you want to run some forensic analysis of large volume of data. It's custom made for that. It's linearly scalable, very low latency, and it has full text search. That was one of the primary reason we chose Elasticsearch over a lot of the other options, because some of the use cases or some of the ways our analysts are looking at, like, hey, I want to search through this. I want to find this IP in blue code, iron port, and some log. It provides a full text search, so it's very ideal for our analyst usage. We have a 3 master node with M4 too large, and our overall Elasticsearch cluster is close to 100 nodes. It's a pretty large, and you can see we are processing 7 terabytes of data. It's a lot of data we are storing. Even if it's 30 days, it's a lot of data. We did run into some issues in the initial part in tuning. Once we got the sharding and all the basic optimizations in place, it's been handling the workload pretty well. And for visualization, or the forensic visualization, we use Kibana, which is an open source plugin for Elasticsearch. Any data that is indexed in Elasticsearch is very easily visualized in Kibana. What Kibana provides you is a custom functionality where you can create a simple dashboard very easily. And it's extremely useful for analysts. With a lot of our cybersecurity analysts don't necessarily have a lot of scripting or programming background. So we wanted to give them an interface where they can create custom dashboards pretty quickly. You don't need programming background again here. And you can add a lot of custom plugins which are available in a lot of open source. Like you have a plugin called as TimeJohn, which lets you do time series charting. There's a Siren Solution plugin called as Keybe, which lets you. So Elasticsearch inherently doesn't let you do cross joins. It's a full text search, so it doesn't let you do joins between two data sets. But there's a plugin called as Keybe, which is available. Once you install it, that lets you do joins between. So a lot of the programming that helped us avoid a lot of the implementation or overheads of building those solutions ourselves. So this is a lot of the data is dummy, but this is how our our ISRM dashboard looks like, where you can look at the total count of destination. You can create nice dashboard pretty quickly using and then you have a full text search bar on the top where you can do just like Google, you can search an IP through your different data sets. The other form of visualization we have for our analyst is the custom real-time alert UI, which we built in-house. Again, as I said, Metron is in the process of providing a UI for alerts, or right now it's being powered on Kibana. For our internal usage, we wanted something more with few more features, which where we didn't have in Kibana. So we ended up building this solution in-house. What it essentially is a case management system for our alerts, where anytime an alert is being triggered based on our business rule, it pops up on this alert UI, and it reflects the right priority. So our analysts, when they are looking at this dashboard, they look at it and they can say, hey, alert has been generated, this is a high priority, or this is a lower priority. It also gives them the visibility if a particular alert is being worked on, is being assigned to an analyst. So they can see which alerts have been opened and needs to be worked on. And on the top, we have a pretty cool SLA dashboard. This is a very unique dashboard which is looked at by our executives or our CISOs. It gives them a good understanding of how many alerts are open, how many alerts are breached the SLA, how many alerts are pretty close to getting breached. So what needs to be prioritized, and how do we look on a weekly basis on our cybersecurity SIC room based on our case management. So the data you see on this alert UI is actually powered by two things. It's powered by our business rule engine, which it's run on every data stream as it's processed through, and it triggers an alert so that those triggers pop up here. And the other way the alerts are generated are through our machine learning algorithms. So the dynamic rule engine, for the dynamic rule engine, we actually used another open source component, which was open source out of Yelp. It's called as ElasAlert. It's a rule-based, Python-based rule engine, which runs on Elasticsearch. What it lets you do is write these small scripts you can run on your Elasticsearch indexes and create custom rules which can be triggered. And then once you create these scripts, you can schedule them both time-based and based on a condition. It's very simple to schedule these jobs. I'm going to be sharing you one specific rule we have created, and internally we call it as a user behavior analysis. Apart from like protecting the data from outside attacks or attacking from looking at external attacks, we also have to look for user behavior analysis, or look at some of insider trading, or some, monitor if a particular Kappa 1 associate has gone rogue. So just making sure there's no inside crooks. So we leverage this technique called as user behavior analysis, which is essentially monitoring your network usage, monitoring your access pattern of your associates, where data is getting uploaded. The rule you see up here is created by one of our SIC analysts, which is called as a high byte out, which what it basically is looking for if a particular associate is uploading a large volume of file outside Kappa 1 network. And you can see on the screen, the creating of the rule is very easy. You can, using the threshold parameter, you can easily set up what should be the threshold which you should be alerted on. And in certain scenarios, there are specific domains where it's perfectly all right to upload. For example, in our working environment, there's a very common scenario where our programmers or engineers are uploading something to our local GitHub. And at that point, we don't want to be triggered for somebody uploading a large file on GitHub. So you can add whitelist domains. So you can you can provide a certain list of whitelists which won't be triggered on this. ElastAlert also provides you a mechanism to forward these alerts. So once the alerts have been identified, once it runs through a data set and it triggers something, you can route it to your you can route it in form of text or email. In our case, we route it to our alert UI, which is being monitored on a regular basis by our security analyst. But there are multiple endpoints where, based on your needs, you can route these alerts to. As I said, we also use machine learning algorithms both for enrichments and for like anomaly detection, identifying a phishing email versus a regular email, or rating unknown domains. Specifically, we have this machine learning model running in production called as DGA, which detects malware callouts as they are happening. I want to make a disclaimer. I'll be going through that model in a little bit detail, but I want to make a disclaimer. I'm not a data scientist by any means. My primary background is data engineering. So I'll go through the model, but there might be certain aspects I might not be able to explain in detail, or might not be able to answer a few questions on data science. So as I said, we have a machine learning model which is identifying malware callouts at real time. So how does a malware actually happen? So what happens is, first your computer or a server gets infected by a malware. When the malware is on your computer, it starts communicating with the command and control center, which has already been established. And once that communication is done, the command and control center starts sending in a list of commands or list of steps the malware has to execute on your machine. And that's how the data breach or a lot of the attacks happen. So in the past, it used to be fairly simple. Once you have identified a machine was infected by a malware, it used to be fairly easy to mitigate those attacks. All you had to do was you identify the machine that was infected, you reverse engineer the malware, find the domain for the command and control center, and you just put it on a block list. So no further machine is communicating with that command and control center. But what happened was, as these malwares started getting sophisticated, they started using a technique called as domain generation. They started using an algorithm called as domain generation algorithm. So what this algorithm does, or what the malware started doing, was like they started generating dynamic domains every regular intervals. So every time, every hour, or say every 15 minutes, the domain used to change. So it started becoming very difficult for analysts or cybersecurity professional to keep block listing these different domains, because every domains were generating on a regular basis. I mean, the DGAs were first popularized by configure attack, which happened a few years ago. I'm not sure how many of you are familiar with configure, but it was a very widespread attack which happened, and it impacted international community. It wasn't just a particular corporation. There were multiple corporations, multiple even government agencies. I think at some point it had infected several German Air Force computers. Like, it was hundreds of German Air Force computers were shut down for multiple days because of this DGA attacks. And what happened was, at that point, a lot of companies and cyber activists got together to mitigate this attack. And in the beginning, they were able to contain it because this algorithm was generating close to 250 domains every day. They would reverse engineer in time, and before the domain was generated, these security activists would go and buy out those domains, and that was their means of mitigating it. But the algorithm kept getting sophisticated, and it got to a point where it was generating like 50,000 domains every hour. And at that point, it becomes physically and logically impossible for somebody to reverse engineer at that pace, identify that many domains, and then buy out that domains. Eventually, they came out with a solution. I don't remember the exact patch for it, but there's a patch came out. But we want to make sure we avoid that situation in real time. And as soon as the malware is infected and it starts generating that, we identify that and we start blocking those IPs. So how does a DGA look versus a normal domain? I mean, if you look at the screen, it's fairly easy to differentiate between a DGA versus a regular domain. It's just by looking at it, you can easily tell the domains on the right-hand side: Facebook, Google, Reddit. They're all well-known domains. They are regular domains, versus the domains on the left-hand side of the screen. They're all DGA or domain-generated domains. So how does a human, or just by looking, how do you differentiate between a regular domain versus a DGA domain? So basically, by answering some of these questions, I mean, does this domain look English or German or whatever particular region you're working in? Also, does this domain phonetically sound plausible? Do I recognize any of the names in the domain, any words in the domain? And do the words make sense together? So what we did was we basically converted a lot of these basic principles into a linguistic-based model, which ran a natural language processing over these different domains and differentiated a DGA versus a regular domain. And to run this model, we limited our data set on domains versus DNS. I mean, for a lot of you on the cybersecurity background, or in general must be aware, the DNS log volumes are fairly large. It's like multifold times compared to if you were to just look at regular domains. And once you're looking at processing DNS logs, you add that much extra amount of data processing overheads you have to maintain. At the same time, there's a lot of latency, and you wanted these machine learning to alert you on a real time. So we limited ourselves to domains versus running these models on DNS logs. For feature extraction, we relied on vowel ratio, digit ratio, distinct character ratio. Then we also took every possible substring of these domains and then matched them with the dictionary, and then normalized the results and saw actually how many hits we got for each domain. In the beginning, I think on a total, we extracted close to 50 features. We ended up using 20 features for the actual model. And in machine learning, I mean, the key factors is always the feature extraction and the training data set we use. So for training data set, for the good domains, for established good domains, we relied on the Alexa top 100 list, which gives you the top 100 domains. And for identifying the bad domains or DGA domains, we actually have an in-house malware reverse engineer, a small group of malware reverse engineers. So we actually created an isolated environment where we downloaded these malwares and we reverse engineered. We created a lot of DGA domains, and so we use that as our training set. So it's been running with an accuracy of 99.7. It looks good, but I mean, even with the 99.7, it's a lot of, when you're processing at a volume of 7 terabytes, sorry. Thank God. So even at 99.7, it's with 7 terabyte of data per day. It's still a lot of optimization we are working on a regular basis. We are improving our features. On an average, it processes close to 30,000 events per second. On any average day, it's 1 terabyte of data in total. It's been running in production for close to 6 months now with zero downtime. We've done a tenfold validation for false positives, false negatives. Oh, seriously? Can I get? Hmm?
You got a lot after. I really want you to click OK.
Yeah. I hope it doesn't start installing something. Oh, I have to finish before it restarts my laptop. Yeah. Yeah, so but now that we had the model, we still had to productionize it. We had to process close to 70,000 records per second, and that's a bigger challenge. I mean, a lot of you guys who have worked in the data science feel like it's building the model by itself is a task, but like scaling it and getting it into production. As I said, Metron provides you a flexibility of model as a service. We had a larger initiative which is more of a machine learning model as a service for our enterprise organization. For that, we build this machine learning model as a service in-house. It's what it essentially is a Spark cluster behind Amazon's ELB. One of the key benefits of that is It's running behind Amazon's ELB, which provides us a static IP. So each time we have to take down a server or we want to scale those clusters, we don't have the end application or end users are not impacted. And we've done some modification or improvements for just because we had to process this data set at real time. So it's running using a gRPC protocol, which is nothing but a very compressed or a faster version of REST protocols. Also, not every data set has to be processed with our machine learning, because we don't have to send Google or Facebook.com each time we find those domains. We want to make sure we avoid that. So we use a Bloom filter-based caching mechanism. So we just limit. So every day we have a data set which is already generated of good IPs and bad IPs, which we don't run, or if a bad IP gets automatically rejected. And also, once this application, which is processing at like 7 terabyte, one of the bigger challenge we had was monitoring. There were a lot of components, different open source components which we had plugged in together, getting operational insight of like, what is your Kafka throughput of, if a particular data set is not processing or data doesn't show up in Elasticsearch, it becomes a challenge of identifying what is a bottleneck. Is the data being clogged at NiFi? Is a Kafka particular topic is not done, or Storm topology is not processing at the right space. So there was a lot of those initial challenges which we ended up solving by, we leveraged a lot of the inbuilt operational APIs which Storm provides or NiFi provides to collect a lot of the throughput metrics. And we also have Jabix agents, which is collecting CPU, memory, IOPS, disk information. And we collect all that data. Then again, similar, we have a separate Elasticsearch cluster where we standardize and create a monitoring dashboard using Grafana. So I mean, it is on purpose reduced because I didn't want to share a lot of our data source and data set. But what it essentially does is like on top, you can see 6 out of 6. It tells you like 6 out of 6 NiFi nodes are still active. So if a particular nodes go down, we get red alerts there. 41 GB is in pipeline in NiFi. The second layer is actually our Storm topologies, which tells you how much throughput for each topology is being going through. So it's a good, just like an analyst, it's our single pane of dashboard, which lets us maintain our operational at real time. And we had some challenges, technical, operational, organizational, while building this product. I mean, for technical, especially scale, which we leverage a lot of the Amazon and cloud solution to scale this application. And rehydration was one which internally in Capo One we have this AMI policy, because again, governed by governance and audit, where every 60 days we have to rehydrate our cluster. So that means every 60 days we have to take down their entire instance, entire system, and then rehydrate it with new AMIs. So for that, we have to actually form a very solid DevOps team. It was, again, a learning journey where we had to Ansiblize a lot of our production environment. We had to create, for Elasticsearch, we had to create tribal nodes where multiple clusters are sitting and which we could route between different clusters. So that was a big challenge which we had to deal with. Security, we actually had to secure this data. And we leveraged a lot of actually, some of the components which were open sourced by Netflix, Bedrock, we leveraged a lot of that for our security measures. As I said, for operational, we built that metrics application. And there were some cultural changes, as I mentioned. It's moving for a financial bank, moving to an open source, embracing that. There were some cultural changes. We had to educate our end cybersecurity customers that it's open source solution. It's not going to work. It's not a out-of-the-box solution which is tested by 1,000 engineers. It's 100 engineers who are contributing at open source at their free time, so it's going to be buggy. So there were some cultural changes. We had to educate, work with our program managers. And recruitment, as I'm sure everybody in here deals with, like big data hiring, some of those skills is so difficult. So we actually have an internal program which we had to launch where we hire a lot of people from fresh out of college from top schools, and we hire mentors. And we pair them. So every 4 or 5 engineers are paired with a mentor. And so we ended up growing up the team that way. This is an overall timeline of the project. As I said, it was launched in July of 2015. It took us over a year and a half to get into production, into stable environment, but it was like powered by our machine learning and rule engine. We launched our first topology somewhere, I think in June of last year. And last 8-9 months, all those Metron topologies and parsing has been running efficiently in production. So what we are doing next is we're taking some of this streaming expertise we've gained by processing this 7 terabytes or large volume of data set. There are other areas in business which have similar volume or needs to ingest similar data set. So we are working on creating something standardized, just not for cybersecurity, but for other finance use cases. That's my contact detail. I'm very active on LinkedIn. If somebody has further questions and want to know more about the projects or get some more insights about the project. Sorry, I ran very close to the time, but I think I have a few some time for questions. Not even for a few questions? All right. I'll be.